Hi, in this video I'm going to show you how to make this. What is this, you might want to know before deciding whether you want to make it or not? Well, this is an electronic puzzle where you have to enter a sequence using this series of buttons on the top, and if you enter the correct sequence these LEDs will light up. When all the LEDs have been lit, the maglock at the bottom will release. Now this is a very common type of puzzle that you might find in an escape room, for example. I deliberately haven't themed it at the moment, so this is kind of the raw electronics, but you could very easily put this into many different themes. You could make these buttons much more interesting than just push buttons like there. You can have as many buttons as you want and as many steps in the sequence as you want. So I'll show you it in action first of all. So if I simply reset the puzzle to start with, and I will secure this to my maglock here. So imagine that that is on a door restricting access to another area, or on a cupboard, or on a chest, or a drawer, something that you can't access, and there is no way that magnet is budging off that at the moment. So with my three buttons I need to enter the correct sequence. If I get a button correct, it will light an LED like that. If I get the next button in the sequence wrong, the LEDs will reset and start from 0 again. So if I go that button, that button, that button, that button, no, that, no, that. There we go. So that was the correct sequence, accompanied by the clang of the maglock releasing. So you can now open the door and get through to the next area. And the LEDs are just doing a chase sequence to show that the puzzle is complete. So now you've seen it in action, I'll explain a little bit more detail about how it's set up, the components I used, and how you can build one of these yourself. So the total cost of components is probably about £15–20, something like that. And the most expensive component by far is the maglock at the bottom. Now this is powered by a 12-volt DC supply, which is coming through this cable here. And you could simply plug this directly into a 12-volt DC supply from a power adapter or something like that, and it would energize and it would hold the magnet in place all the time. And then when you cut the power, it will release the magnet. Now we want that to be controlled through the program that's running on the Arduino. Now Arduinos run at 5-volt logic supply, so they can switch 5 volts on or off as a way to control other components. And this is a relay, which you might be familiar with. Relays are just like an electronic switch. So rather than a light switch which you activate with your fingers, a relay is activated, or this relay is activated by a 5-volt supply coming from the Arduino. And when it detects that 5 volt, that's the equivalent of you pressing the light switch, it lets 12 volts run to the maglock at the bottom. So that means that the Arduino never has to deal with any high voltage circuitry or anything. We're all at 5 volts over here. This is the only thing running at 12 volts. And the relay provides the isolation between them. Then the actual input itself is quite straightforward. I've got these 3 momentary push buttons here, so you press them and while you're holding them they will be in one state, and as soon as they release they'll go back to the default state. Now I'm using something called the pull-up resistors on the Arduino. So these are actually wired so that when they're not being pressed they read as a high logic signal, so they read as 5 volts. When you press them, what they do is they actually connect these input wires here to ground at the top, and it will drop to a low logic signal. So it's kind of the reverse of what you might expect. They are high by default, you press them and they change to low, and so I can detect which button is being pressed. So those are 3 inputs. Like I said, it'd be easy to extend that to any number of inputs. And then I've got my 5 LEDs, which are simply outputs from the Arduino, and they are being run through 240 ohm resistors, just to limit the current going through the LEDs so that I don't blow them with the Arduino. And then we've got the Arduino itself. This is currently being powered from a USB cable from my computer, but it could be powered by a battery or through the barrel jack to any DC supply. But we'll keep the supply isolated from the 12 volt that's going to the maglock. And in your room, in an escape room itself, they may be physically some distance apart anyway. So I'll show you the code that runs on the Arduino, and it looks like this. So we start off just with a simple define. That's always a useful way if you want to include debugging information in your code, but you want to possibly strip it out when you run a production thing. So just do a define, and if that is in the code, then there'll be some additional information come out to the serial connection if you need it. Then we move on to the constants. So this section here is things that are not going to change at all while the game is running. So this is the number of buttons that the player can press. I'm using 3 at the moment, but you could easily extend that. And these are the pins on the Arduino that those 3 buttons are connected to. So we know how to sample the player input. This is the number of steps in the puzzle, so the number of button presses that need to be pressed in the right sequence. And this is actually the sequence of buttons itself. So obviously it's 0 based, so this is the 0th button, is the first button that players need to press, and then the second button, and then the first button twice, and then back to the 0th button again. That's the correct sequence that players need to press to unlock the code. We then have the 5 pins that the LEDs are connected to, so that's obviously equal to the number of steps in the puzzle, because there's 1 LED gets lit for each correct step forward. And finally we've got the pin that the maglock is connected to, or rather the relay is connected to, that will then deactivate the maglock. So like I said, I'm using internal pull-up resistors on the inputs, so the default state of all the buttons when they're not being pressed is logic level high. And we assume that we start at the beginning of the sequence, so the current step is 0. Now, this next bit here, there's one of the problems you can get when you're reading button inputs in any electronic system is something called bouncing. So a mechanical switch, when you press it down and make the contact, and when you release it again, can generate a little bit of bounce, which is literally where the signal kind of flickers on and off momentarily every time it changes state. Now that's not massively a problem, but if you're listening for an exact sequence of buttons being pressed, obviously you want to make sure you're not picking up erroneous releasing or pressing of the button, because that will kill the detection of the correct sequence being pressed. So there's a couple of different ways you can approach that problem. This is kind of a very simple one, which is to record the last time an input was received and then define a delay before we then attempt reading another input. So this is 50 millisecond delay, which is enough time just to make sure that if the switch is bouncing around a bit after changing state, we're not picking up that noisy signal. We'll wait for a clean signal before reading it again. So here's the setup function that runs at the beginning of the code. We activate all the inputs that have got the buttons connected to them as input pull-ups. So that means that they'll read high when there's no signal. It will pull the signal to high rather than it just being a floating pin when nothing's pressed. Here we activate the LED pins as output, and we've also got the relay. The lock attached to the relay is an output switch, and we'll activate that as high. So my maglock is plugged into the normally open connection of the relay, so unless the relay receives a signal of high, it will be unlocked by default. So we'll send a signal as high when we want the relay to activate and we want the maglock to close. So that's the default state of the puzzle while the puzzle is in play. And this bit here, this is what I was saying about if you want to print a bit of debug information while you're just developing the puzzle, we'll check for whether that define is there in the code or not, and if so, we'll just print a little bit out to the serial connection. And then here we've got the main game loop. So this is that debounce I was talking about. We'll just check that the current time that the program's been running for, that's what millis gives you, if that is greater than the last time we read a signal plus the debounce delay. So we'll only read it if it's been at least 50 milliseconds since the last input. We'll then read through all the inputs and get their current state. If it's different from the last state that we read for that input, then this has been a change in this frame here, so we'll reset the last bounce time to this time. And then if it is currently reading low, but it was previously reading high, that means that we have pushed the button down. So we'll then check whether the input that we've received is correct for the current step in the sequence array. So this steps was the array of correct buttons to be pressed. So if the button that has been pressed this frame is equal to the current step that we're up to in the sequence of steps, then we'll move on to the next step. That's what that says. And we'll put a bit of debug information. If the index of the button that was being pressed this frame is anything other than the next step in the sequence, then the player has entered the wrong input, and we'll log that and we'll just put it back to the beginning. So we set current step back to 0, so that's resetting the puzzle, and we'll just log some output. And we'll just update what our array of the current inputs for each button is. If the current step is equal to the total number of steps in the puzzle, we'll call this trigger here called onSolve. So that's just a little method that will get called whenever the puzzle is solved. And the last bit we do is just to give the player some kind of visual feedback on how they're getting through the puzzle. We'll loop through the LEDs and light each LED up to the number of steps in the sequence we're up to already. So if we're up to step 3 in the sequence, we'll loop through the LEDs and we'll light LED 1, 2 and 3. And then here is that callback that happens when the puzzle is solved. So we've got we print a debug message to the screen just to say puzzle solved, or back to the serial connection rather. We release that door lock, and then this here, because we've got while true, this will loop forever. And what that simply does is that will flash through the LEDs in turn in a kind of a chase sequence. And that is the whole code. That's all there is to it. So I hope you found that useful or interesting, or preferably even both. Like I say, it's not a particularly complicated example, but it does introduce a lot of common elements that you'll find in other escape room puzzles. So inputs, outputs, relays to control other circuits, code and debug information. And it kind of forms the basis from which you can actually go on to create more complex puzzles. But even this in itself could form a pretty fully functional puzzle if you just dress it up in a little bit more thematic kind of covering to make it fit into your game. If you'd like to download the code I used, or if you want to access a wiring diagram rather than sort of looking at this, then please look in the notes in the description below this video. And if you'd like to see me demonstrate any other sorts of escape room puzzles or other electronic things, please write a comment and let me know, and I'll see if I can do that in the future. Okay, cheers, bye.